Okay, everybody, welcome back to day number 2. So today is actually not going to be too bad. Yesterday wasn't too bad, but as a student, as a teacher, I can say it's not too bad. As a student, I can say that's probably a different perspective. But anyway, so we're going to start in with 2 programming languages today. The first one we're going to look at is Scheme, or Lisp, and the second one we're going to look at is Prolog. Probably won't get to Prolog till tomorrow. So we'll see what happens, because we have 2 activities we need to do today, and we have kind of a short half-day kind of format going on today. But don't worry, we'll get everything done. So what you're going to need to do, what we should have covered this morning, that I'm going to save you the boredom of covering, would have been lecture number 4 and lecture number 5, going through all those searching algorithms. So if you read the chapters on informed search and uninformed search, and if you remember what I was talking about towards the end of yesterday, that would have been the stuff I would have covered this morning. Instead, I'm going to kind of wait. I might get to it eventually, but I'm going to put a higher priority on Scheme. So the lecture I'm going to do right now is from the bhacker.com website, and it is the one that is titled Lisp, L-I-S-P, tutorial. So I'm going to go through the tutorial, and about halfway I'm going to stop. We're going to download, and I have a Windows partition on this computer. So I'm going to download Dr. Racket, and we'll see the examples work. And so you'll be able to be functional. You're going to learn a new programming language today. And I'll tell you why you're going to learn it in a few minutes when I start the lecture. But that's the game plan for this particular lecture. So if you download the lecture AISLisp.ppt, that's what I'm looking at right now. So what is Lisp? Let's see if I can get started first. Here it goes. Brief introduction to Lisp and Scheme. The 2 languages are very similar. So back in the 1950s, people had all of this data. And we talked about data and knowledge representation yesterday and data representation. So the data is on the computer, and we want to use the computer to help us analyze the data so we can artificially figure out stuff. Trends and weather patterns, I don't know. What member of this list is also a member of that list? And so Lisp came around. So Lisp is for list processing. It takes an entire list of information, compares it against another list, sorts the list, searches the list, performs a lot of automation that would otherwise be very tedious. So it's an attempt to sort of automate the AI concept of sorting and searching through the data. So the concept of assignment is not part of functional languages. And by the way, this falls in the category of a pure functional language. It's functional because it's function-based, and you don't have to know anything about programming, anything about any of the languages to understand all this. In fact, the people who use Lisp, Scheme, and Prolog are not computer science people. They're artificial intelligence researchers that use these languages. So no prior programming experience is required. So what do we got here? We have no assignment statements. We have no variables that are bound to any values. So all that stuff, even if you know programming, all that stuff's not going to help you anyway. We have function calls that have no side effects. We have no global state. So we also have, in terms of flow control, there's no iteration. There's no repetition, but there is recursion. So for those people who know about recursion, they always go, they always usually shake or do something. Oh, I don't like recursion. Don't worry about it. It's actually not too bad with this language. So we have what's called referential transparency. This is just your vocabulary today. And it's the value of the function application which is independent of the context in which it occurs. So the value of function A, B, C depends on only the values of A, B, and C. So every time you run the values with the same function with the same values, you get the same response regardless. So it always acts the same way. All variables in functions must also be local. There's no global scope. There's only a local scope with this. And there's nothing that depends on the global state. Everything is separated out in terms of its functionality and in terms of its scope. If you want to think of it, scope. Also, another characteristic of pure functional language is that all storage is implicit, so there's no copy semantics, which needs garbage collection. And we're going to see how that works actually with Scheme. But the concept is we just fill the memory up. We fill the memory up, and then eventually we're going to have to dump the memory out because we're going to fill it up too much. So functions are also first-class values, so it can be passed as arguments, and you can be returned as values of expressions as well, and can be put in data structures. It can be used for multiple different purposes. So I'm going to kind of skip through this because this is 160 or so slides, and you don't want to go through all this stuff and everything you ever wanted to know about the language. Instead, I'm not going to compare it. Instead, I'm just going to get right to the nitty-gritty details of what this language entails. Okay, so it was not made for programmers. It was made for scientists. It was made for math people, made for data crunchers. So they love Lambda expressions and Lambda calculus. You guys don't like that because you guys are programmers. You like, so there's an alternative choice, however. The current IDEs come out will allow you to use variables, allow you to use things that you're familiar with, and not have to worry about the Lambda calculus. However, I sort of need to explain what this is so you kind of have an idea about how the function works. So mathematical functions is a mapping of the members of one set called the domain set to another set called the range set. So for the domain, we're going to match it with this range of values that we have received from our experimental results from our AI experiment that we conducted. And so we're taking one set and we're matching it with another set, or we're applying a function to all of the values that we have received from a particular set. So think about sets of data, think about lists of data, and functions that might be performed on those data, which is what this language does. So the Lambda expression itself specifies the parameters and the mapping of the function in the following form. So we have the Lambda expression of x, which is really the function of x, which is equal to x times x times x times, 3x's, x times x times x, which is x cubed, if you think about it. But we have this for the function. This is what you're probably going to read. This is what you're going to write. This is what you're going to use. You're going to say cube. But in the beginning, they didn't have, the concept of naming a function. So it just says declare a function. And in the old days, we used to have these symbols that we could actually just, put in there, click on it. So modern day keyboards, I don't think that expression is even on the keyboard anywhere. I don't see it on my keyboard. So basically would have to work with old antiquated kind of environments to actually even write with this syntax if you were programming this way. So this is the expression here, which is basically the same. This is nameless, this has a name. So you're probably going to be naming your stuff, and we'll see in a few minutes how this stuff works. So the Lambda expressions are describing nameless functions, which is really the equivalent. So these two are the same, by the way. And this is going to say the function of x. So the f of x is going to be equal to, and this is, I'm going to go back to Algebra 1, I would say, and then you'd get the concept. Or maybe this might even be pre-math, pre-algebra, I don't know. But anyway, Lambda expressions here also apply to parameters. So by placing the parameter in the expression here, 3, we apply 3 and substitute for x. So it's kind of interesting. We create the formula, which is, the scheme is very similar to MATLAB, which is very similar to some other functional programming languages that are used for mathematics or used for automation of certain calculations, which is what they're used for in artificial intelligence as well. So here if we substitute 3, and then we have 3 times 3 times 3, which is going to give us a value of 27, and here 2, so we substitute 2 in. But this is a different expression. This one has the value 2, so it would be 2 times 2 plus 3, and we get our response out of that. So it's strictly function substitution from pre-algebra math or algebra, whatever. It's not rocket scientry. It's not hard stuff. Function forms. So in Lisp, we originally started out with 3 function forms. We had the function composition, the construction, and the apply to all. So imagine you're not learning a programming language, you're learning a function system. And you have this list of data and you want to apply some functionality to it. Well, you have 3 to choose from in this basic system. So in this function form, we're looking at a higher order function as one that either takes functions as parameters or yields a function as its result, or does both. So we were sending a value here, 3. Well, we can send a function to the function to the function to the function. We can also have the function call itself over and over again. So we can do an automatic Fibonacci calculation, a summation, all sorts of different neat stuff if you like recursion. So the function composition, the construction, and the apply to all are the 3 categories. So the function composition is to compose the function. In this particular case, a functional form that takes 2 functions as a parameter and then yields a function whose result is a function whose value is the first actual parameter function applied to the result of the application of the second parameter function. We do this so we can stack it all up. We don't do this to make it more confusing. We do this so we can stack up everything to automate it. Because if you think about the concept, you have a list of thousands of items and another list of thousands of items. You have to run a function on it first, and then you have to run a function on it second, and then you have to apply the second to the first, or you have to figure you're going to have two separate functions maybe that are running with this. You stack it all up into one function call, and you say go. More automated than having to say, okay, here's the results from the first function return, and let's apply it to the second function return, and then let's apply it to the third function return, and then all of a sudden you go, oh, we applied the wrong one. Too much room for mistakes. So if you can condense it all and do a function composition on it, you compose the function of other functions, and you have one function that you're running. And you save the function in a text file, you load it up into the language system, which we're going to see in a few minutes, and then all of a sudden, you know, hey, it works, hopefully. So here's the form here. Don't get caught up with the syntax. In fact, that's an interesting symbol, the question mark inside of the diamond. It means the symbol's not here in my slide set or my fonts. But anyway, look at the bottom line here, actually. If f of x, if you're going to run f of x and you're going to send g to f of x and g of x to f of x, you're going to run the inside and then you're going to run the outside. So just think of it more like you're sending a function call as a parameter to a function. So you're going to resolve it down from the innermost parameters. It doesn't really matter what order the parameters are evaluated in. So you can't really assume it's left to right, right to left. It doesn't really matter. They might be both done simultaneously if you have enough memory in the system, actually. So here, if we have a f of x, and if that one equaled 2 times x and g of x was equal to 1 minus x, if we ran f of x with g of x as a parameter, then we'd say f of g3 is equal to f of g, g to sending 3 to the g function, and then sending that result to the f function is what we're essentially doing. So 3 times 2, what do we have? 6 minus, well, we got 5. Well, okay, we got the wrong number here. 3. Well, anyway, you get the idea. Run the parameters first, and then substitute the parameter values from the expression into the outer expression. In terms of the construction, actually here it is. Here it's a better way of presenting it. Makes more sense. So the function form that takes a list as a parameter is a list of functions as a parameters as the parameters, and then yields a list of results by applying each of all of its parameter functions to a given parameter. So here we have the form f and g that are part of the function call. And then f is x times x times x, g is x plus 3. This is the second form of the function, by the way. So we have the construction, we have the function composition as the main form, then we have the construction where we're going to yield. If we put 4 in here, 4 is going to be applied to the f, and then 4 is going to be applied to the g. We're running a string of functions for the data because we want to run multiple functions, one right after the other, or maybe simultaneously on the data, and we want to yield a final result. And then in this particular case, we'd get 64 and 7. We'd take 4 plus 3, and then we got 4 times 4 times 4, so we yield the 2 results. This is called the construction, where you're constructing a call to a function that consists of function calls, and you're applying a list of data to that list of functions that you're going to use in here. Don't worry about it. We're going to show you some examples, and you're going to see it work together. This is the one that's probably the most popular. It's to apply to all. So you have a bunch of strings, and you want to convert them to floats. Or you have a bunch of strings, and you want to find out the average of all of those, or integers or something. And so we don't have types in this language, so we don't have strings and floats and doubles and stuff. We just have data, so which is nice because it's not a strongly typed language, so we don't really care what we have actually. And the list can contain a number, a string, anything it wants. So if we do an apply to all, and I'll get into that concept in a few minutes. If we do apply to all, the function form that takes a single function as a parameter and yields a list of values obtained by applying the given function to each element of the list. So here we go for the form for x of h, which is x times x times x times x. Apply here h to the numbers 3, 2, and 4. So for this data, we're applying this function to it, so we get 27, 8, and 64. That's all you're going to need to really do in this class. You're not going to have to do anything else except, well, actually one of the assignments is going to ask you for a recursive function. And I'll go over that actually in a few minutes. I'm going to go over the first two assignments today as well, so we know what we're supposed to be doing. So that's essentially the mathematical basis for Lisp. And then we ended up with another language called Scheme, where we were able to define functions. I'm going to skip ahead a little bit and talk about Lisp first. I'm not going to worry about the fundamentals of functional programming languages. You can go ahead and read through this a little bit slower if you'd like. So Lisp, as a language, that's the basis. That's the entire language, by the way. I just gave you the whole language. So that's what the language does. Not a big language. It's very small. So functional languages developed in around the 1950s. This guy, John McCarthy, put this one together. The semantics are based on Lambda calculus. So Lisp was all Lambda calculus. Not very user-friendly. I mean, it was not. And it only had 6 basic functions. And the 6 basic functions, we're going to see some examples of this today, but cons, char, CDR, equal, and atom. And then we had conditions. Well, we had just one condition. It's like the if-then, if-else kind of condition. Not too powerful. But it was useful for list processing, useful for artificial intelligence applications, and programs that can read and generate other programs out of that. Because you can send a function to a function and you can get different results from different patterns. So the idea was to put it together and then run your data through it, and you'd have like a really good way of comparing the data sets. If you ran it through in an automated way, you're guaranteed to have the same calculations performed on each one regardless of who did it. So you put it into the program, you loaded up the function, put the data in there, and then 2 weeks later you put another set of data in there, and 2 weeks later you put another, and you have really pretty good consistency among your apples and apples, because one of the worst parts about doing research and data in terms of an AI, because a lot of these problem solutions come out of research and analyzing the data, is that you don't know what you're looking at. You get data that, oh yeah, we did this to that data, and this to that data, and then it's a total waste of time. So it's really important actually to get some consistency in your results. Otherwise, you don't know if what you're doing is really effective. So Common Lisp was the first dialect of Lisp back from the 50s. It was implemented. It did not completely adhere to semantics. It sort of went off, and people say, "Oh, Common Lisp." Try to make it a little bit easier. So semantics that were redefined to match the implementation. Some of the wording was changed around. So Common Lisp actually became the standard for Lisp. And then Scheme came out of Lisp. So Scheme as a language in the programming language trees started at the top. Lisp started at the top. And then Lisp branched out into Common Lisp and then Scheme. They're both 2 languages that are dialects of Lisp, which is kind of interesting. Many defined functions, simple syntax, large language. Here's Scheme. Scheme, this was about the 1950s. Lisp is around the 1950s, late 50s. Common Lisp was around, it didn't get unified till 1980. Scheme is around 1970 to kind of give you some perspective on the development effort. The mid-1970s dialect of Lisp was designed to be cleaner, more modern, simpler version, more contemporary. Not Common Lisp, which was kind of cryptic at the point. So it uses static scoping. Functions are first-class entities as well, and it turned into a first functional programming language. So from programming language concepts perspectives, this is one of our first functional languages. It was like the predecessor of a lot of our current functional languages that exist. ML is an example. MATLAB is another example of functional languages. So there are values of the expression and the elements of the lists that are contained, and it can be assigned to variables and passed as parameters. And basically all the functional referential integrity and stuff that I looked at before, that I was showing you in those examples, applies towards Scheme. So the basic workings of Lisp and Scheme are how the expressions are demonstrated. So this is slide number 16, which is the start of the programming expressions. So what I'm going to do is kind of pause this moment here, install Dr. Racket, which is our Scheme version, and then we can see this stuff live. Actually, we can see it work, hopefully. So I'm going to make this a little bit bigger, get rid of this bottom screen. So most of you guys have Windows. You can install this on Windows or you can install this on the Mac. The process is the same, and I'm going to show you how. But I'm going to demo it on a Windows because I'm looking around and I see a majority of Windows computers. So, not to worry though. You can install the same program on the Mac, and here's how we do it. So we're going to open up Google because we have to download it. Hopefully you have an internet connection. Let's see. I bookmarked it here. If you don't, actually, if you don't want to, let's not do the bookmark. We'll just go like this. We'll do the bookmark. I'm sorry. In your Internet Explorer, or in your Firefox, or your Chrome, or your Safari, or in whatever it is that you might be using as a web browser, go to racket.lang.org. Dr. Racket is the current version of Dr. Scheme, which is the current version of Scheme from one area of research. We have GNU Racket, or GNU Scheme. Works better on the Mac, actually, the GNU stuff. This one works better on Windows, but I believe they're both compatible, and the windows look the same. When you get to this URL, does anyone need this URL anymore? Hopefully you can see it's kind of light. The glare up there is kind of light. Everyone got it? Okay, who's going to do it? Okay. If you click on the Download Racket button right here, right underneath the Download Racket, you'll see Platform. If you click on the platform, you'll see OS X. You'll see the source here. You'll see up here OS X, Intel 32, PowerPC, OS X, Intel 64-bit. Depends on the book you're on. Most of you probably are going to be over here in the 32-bit or the 64-bit. So it depends on what you think you might have. If you're a Windows person, I'm on XP. So I'm going to be on a 32-bit XP system. It's not going to tell me. It's just one Windows version. It works on everything. So if you're on 7, that Windows version works. If you're on XP, it works. So while you're doing that, so select the operating system you want. Click on the big download button. And you'll see a little thing pop up. No little thing popped up. Now, let's go. Oh, yes, here, I'm sorry. You have to pick the download site. You get taken to the mirrored site. I'm going to pick a mainland download, Massachusetts. Now the little dialog comes up. Save it to your desktop. Let's see. I'll save it to my desktop. I'm going to reinstall it. So I installed it earlier just to test it, but I'll reinstall it so you can follow through. Now while this is downloading, I'm going to show you something else. I'm going to open up another web browser window. Don't have to do this, by the way. I just want to show you your choices. And this might take a few minutes because everyone's downloading it. But if I go to Google here, and I type in, and I'm just showing you another alternative here. GNU Scheme. And I go here to download, or actually I probably could have clicked on this one right here. MIT has a current GNU Scheme project out there. You don't get the same GUI as you get with Dr. Racket, which is, you're going to love the GUI in a few minutes. You're going to see what I'm talking about. This one here is command line based. It mostly works great on Linux and Unix. And it works on the MacBook just fine as well. And it does have a slight GUI interface to it. I don't like it as much. It's not as user-friendly. But if you want, you can experiment with this one too. This one used to actually be installed on early PowerPC versions of, what was it? I can't even remember what it was called now. The Apple operating system, like version 7 or 8 before we got OS X. I can't remember what it's called right now. But anyway, long story short, it used to come, just like Python and Perl actually still come. So does PHP. No more PHP. But we still get Python with current OS X. This was one of those experimental languages that's free. It's always been open. I shouldn't say free, it's open source. So a lot of people are developing it. MIT people are developing it for their AI research lab. And they have different libraries that are supported in there. You're going to see when I bring it up that there's a couple of different options and a couple of different languages of Scheme. There's no standard to this. It's developmental language. So back at the ranch here, I'm going to wait for my download to complete. Shouldn't be too long. When the download completes, this install takes about 5 seconds. And once the install happens, then we configure it with a language. Is everybody downloading this? Is this why it's running so slowly? Okay. Alright, so as soon as some of yours quits, mine will run faster. So meanwhile, back at the ranch here, we'll go back to the PowerPoint. So basically what we're looking at is an infix. So it's an infix parenthesized form of an expression. So most people like the idea of going 1 plus 1, and then they press return and it equals to 3, equals to 2, right? So now you have to get used to this form here, plus 1, 2. And then you're going to get 3, hopefully, back out of this. And you're going to use parentheses here with every one of your expressions, because what you're really doing is running functions. And the functions that you're calling are using standard symbols, and here we have plus and a minus. We could actually type the word add instead. But there's a common dialect that's being used to kind of, and I'll run these examples and we'll see this in a few minutes. Oh, I heard someone's end. Okay, good. So as yours is ending, mine's going to end. Mine's going to get faster. I cannot believe that we don't have the bandwidth for everyone to download this. But I shouldn't complain, actually. I was at the GMIC conference earlier, and we had the same problem with something else. There was no internet access. I mean, everybody was on it, and they were all downloading a PDF file I told them to download, and it was just like this. It was like, you'd think, San Jose Convention Center, you'd think they'd have better internet access, but apparently there's limitations. So, alright, so I'll give it a few more minutes, so be patient. So what we're looking at then is running functions, and we have built-in functions, and here we have length, which is a built-in function that gives us a length. And then we have this little apostrophe here. The apostrophe here says treat them like variables and not like functions. Treat them like menu items. So, and we'll see that actually here. I'm going to skip ahead a little bit, explain about the apostrophe and come back, except for I can't get ahead a little bit. Here we go. So here's our apostrophe, so our constants. So to get Scheme to treat an S expression as a constant rather than as a function application or name reference, you precede them with this apostrophe. So apostrophe 1, 2, 3 gives us 1, 2, 3 as a value. And this is going to be a list of parameters that we're going to look at. And apostrophe A is going to give us a value of A. So that's actually a shortcut because the original Lisp said quote. We went quote A, so the apostrophe is a lot easier actually when you think about it. Nope, still working. We're good. Still working in the right direction. So what we're looking at then is the basic workings. So operational schematics is to evaluate an expression. So we type an expression in and then we get a response back. It's purely interpreted, which means we don't write a program like we do in an imperative language. We don't have main, we don't have variables, we don't have anything like that. So you evaluate a function to a function value. You can evaluate an argument of a value to a value, or you can apply a function to all values. So the Scheme treats the parenthesized S, as we saw here, as the function application. So the parenthesis here is an application of a function. It says run this function. So if you're an Objective-C programmer, you're sort of familiar with this, and you have to think Objective-C came out at the same time period, but they used brackets instead of parentheses. And the syntax is actually the same. This is a function or a method plus. Send me the message 1 and 2 to plus. It's very Objective-C-like because it comes not from the same language hierarchy, but from the same time period, and that's the thinking that was going on at the time. So.
There can never be a negative number.
You can have a negative number. Why not?
Like plus 1, then minus 1.
We'll do that in a few minutes. But yeah, it's a value. As long as you don't put a space in between. I'm going to show you something about spacing in a few minutes too that's going to hopefully save you some time and energy in the end when you start writing this stuff. So mine's almost done. So apparently some of yours is almost done too. Half the room, I probably was the last person to click download is what the problem was. 88, 89, in anticipation, I'm going to close this window here. Oh, I'm almost afraid to close it. Okay. And this is, that's a scheme function actually. Here we go, 92%, we're getting there. 93. Alright, so 1, 2, 3, we have an error in this particular case because the object 1 is not applicable. There's no such thing as a 1. So if we actually typed in 1, 2, 3 here, without putting the apostrophe here, we were not doing it. We're trying to apply 2 and 3 to the function 1, and we'd actually get an error message. So 99, almost there. So there we go. So I'm going to assume everybody else has beat me to this. So I'm going to double click on it, run through the install for you real quick to tell you what to do, which is really easy actually. So here we go, Dr. Racket. I'm going to go next, and I'm going to put it in the Racket folder here. I'm going to go next, and it's going to tell me there appears to be already Racket in there. So no, I'm not going to install it first. I'm just going to click on yes. And, oh no, I have to uninstall. Okay, let me uninstall real quick. You don't have to uninstall if you don't have it installed. But unfortunately, I have to uninstall it right now. I probably could have just left it, I guess. As you can see, it's loading a bunch of files, and it's an old Windows program, actually. So it's not using the registry. It's not using, it's just a bunch of individual little files that it's storing. Anyway, while this is going on, I'll proceed forward here. So we know about the constants versus the values. And so we get the constants by using the apostrophes. It's just shorthand for the quote. And then we also have this thing called a conditional evaluation. So in a conditional evaluation, it's sort of like an if-then-else scenario that we get in regular evaluation of other functions. So if a condition, then a condition, else a condition, which is the same form that we're looking at if we start using the cond, C-O-N-D, which is a conditional expression, a conditional statement. We'll see examples of this coming up. And here's this condition that x is larger than 0. And in here people go, well, how do you know you write it like this? Well, because x is larger than 0, because we're applying the larger than evaluator with the two items x and 0, which is how we're going to come out with that. And then taking this here and applying it to this to say, okay, well then take this and divide it out by, well, what are we going to divide out? We're going to take 100. So the condition is comparing these two with 100 divided by x, or x divided by 100, depending on how you're reading it. And then we're going to say, well then if x is equal to 0, then return 0, else take 100 times it by x in terms of the expression. So, well, that's one of the things you sort of have to get used to. Dr. Reagan says you can not, yes, force it. I don't have it open. Okay, good. Okay, so if you're running through the install, I'll run it from the beginning so you can see it correctly now. Run. Most of you are probably done with the install. Hit next. Hit next. There we go. Select the directory you're going to put it into. I'm just going to put it into Racket. Hit install. And then wait a few minutes while it puts all those files back that it just took away. Moving right along. So what do we have next? Defining a function. We can also define functions with names. So in this particular example, this is the one I'm going to use actually. We're going to run factorial. So this says define factorial x. So the basic function form for defining a function looks at the word define as in terms of the keyword that says we're going to define something. We can only define functions. There's nothing else in the language, so there's a no-brainer here. We give it a function name, we give it a parameter list. So function factorial is the name, x is going to be the list of parameters, and then we have the function body. And so we don't have like the opening and closes, squirrely brackets and stuff because we don't have scope. We just have local scope for everything. There's no scoping environment with this. Instead we say if x is equal to 0, return 1. So we have an implicit now else, run. And then here's our recursive part for those people who don't like recursion. We're running factorial inside of factorial, and we're saying x minus 1, essentially. So we're minusing 1 from minusing x. So let's see, I'm checking to see how fast the install is going. All right, so now that was it, that was the install. So click on Finish to run it, and it will open up. If it doesn't open up automatically, go to the Start menu, Programs, Racket, and then you want to click on Dr. Racket. When you click on Dr. Racket, you see this coming up here, which is the Racket logo. Half of you hopefully are here already. I'm probably the last one. So it takes a few minutes. This is loading in an emulator on top of another operating system with some recording software going on, which is why it's running so slowly. Yours will probably run faster, and your download probably run faster as well. So once it opens up, we're going to get this funny looking screen that shows up. It's not very user friendly. So I'm going to explain the screen to you in a few minutes here. There we go. And the first thing it's going to do, oh, it didn't do it for me because I already have a language. It's normally going to take my current settings, which is weird because I uninstalled it. But anyway, down here on the bottom, you're going to get something that's going to say, hey, it's going to ask you for a language. It's going, what language do you want to use? So if you click on the language menu item on the top, and you say choose a language, you're going to get this little screen that comes up, and it's not going to be very user-friendly for the most part, because it's not going to describe, well, what are all of these languages I can pick? It used to be in the past we had these teaching languages, and the teaching language was beginning student, which is not bad, or beginning student with list abbreviations wasn't bad, because what ended up happening, here's with Lambda expressions, we had advanced students, and what ended up happening originally is the people that were supporting this and writing this, well, they were teachers, and so they were writing special dialects of the language for their AI students to use in the lab. And they're basically augmenting the language with these different choices. And then, so most of them do everything. Only problem is the level of error checking, the type of responses you're going to get, and the support for, in this particular case, Lambda expressions, which you don't get in some of the other ones. So here's the language you want to pick. And it's going to say, well, it's not one of the teaching languages. You want to go to this one here, R5RS. If you don't like this one, you can pick Lazy Racket, actually. Lazy Racket will have a few things where, shortcuts to it that are built in, but you're not going to know what any of them are. The R5RS is one of the traditional legacy languages that's very true to traditional scheme. And all of the lecture set examples follow this language. So if you select it, then you're going to see language RSR5, and then you're going to see memory 128 megabytes or something similar. Maybe you'll have higher memory footprint. It takes a percentage of what's available on the RAM, and it sets a memory. You can increase the memory to anything you want it to have, actually. For the purposes of this course and what you're going to be doing with the assignments, you can leave it on the default memory. You're not going to run into memory problems. When you run into memory problems is the fact that there's no garbage collection. So if you have a big old list of memory, big old list of items, and you load them all in, because this is very compatible with text files. So you're going to load it all. You're going to fill up all your memory, and the more memory you've filled up, the slower the system's going to run because you don't have that much working memory left, and eventually you're going to run out of memory. So if you ever see the word delay, delaying or something, or wait, or paused, or it means it's trying to figure out what to do because there's no more room left in memory. So that way you increase your memory. So now that we're in Racket, if we want to switch the language, we have this little thing on the bottom, but you don't want the error message anymore. If you have an error message, it's not going to help you with anything. Huh? No frills. Is that what it says? No. Yeah, take the no frills.
No.
Oh. Oh, hold on a second. Let me take a look real quick. I'm sorry, what? Oh, that's perfect. It's perfect. But you see, press return up there. That's an old message. close it and open it back up again. Close it and open it back up again. It should, it's not processing it for you because it doesn't know it. So it should come back and say something like this. And if you close it, if it's not coming back, close it, bring it back up again, and it should be resetting it for you. It should show the language. If it's telling you haven't picked a language, it can't run anything. Is it working now? Okay, good. Unfortunately, I closed mine. Just to say, close it. Don't, do as I say, not as I do. Don't close it. So you have to bring it back up. All right, so now that we're back up here, momentarily, I'm going to show you how to use the screens. There's two screens to choose from, the top and the bottom. The Lazy Racket uses a format in which, and this is the format you'll probably end up doing anyway, is that you can load something up into the top screen and then run it in the bottom screen. Or you can load it all in the bottom screen. So let's run our first function. So if we type in opening bracket and I go plus, and I go space 1, space 2, and I put a closing bracket in there, you notice that the entire expression gets highlighted. And if you press return, I see the answer down here. It says 3. This is a function that you've just run. You've added 1 and 2 together, obviously, but this is the function name here. So I could do this. I can put in and everything you're running is going to have an opening and a closing bracket. It's all going to be, oh, you can see it, that's good, all the same syntax. So I can go length as an example, which is another function. And I'm going to go here, and I'm going to treat this like a set of values. So I'm using this apostrophe that I saw before, and the set of values that I'm going to put in this apostrophe are going to be 2, 3, 4, and then I'm going to press return, and it's going to go, well, what happened? I didn't finish the expression. And the natural thing you're going to want to do is put a semicolon, which I did actually just myself naturally, and I caught myself at that. There's no semicolon at the end of the line. Instead, you have to close the expression, because this expression could go on for days, months, years. Well, for as long as you're going to be rewriting this thing. So I closed the expression, and now you see that the whole thing is highlighted automatically for me. So if I take the expression off, it's not going to be, well, okay, so it's a bad example because, oh, there it goes. This is highlighted because this is recognizable. And if I come back over here, that's not going to be highlighted, but this one's highlighted because that's recognizable. So that's the level of error checking it tries to give you. So if I close it and then I press return now, I get 3 again because it evaluated these 3 items instead of sending this to this. So if I do this and I go length 1, 2, 1, 2, 3. Oops, let me close it again. It's going to come back and give me my first error message because I'm sending a function to a function as a function argument to a function. Well, not only that, but my first function is wrong. This function is incorrect because there's no function 1 defined in the language. And I'm sending arguments 2 and 3 to 1. I don't understand that one. And then I'm also sending this to this. So it doesn't understand what this is, essentially. But I could actually send the length, make this a correct function. So the application, not a procedure, expected a procedure that can be applied to an argument, given 1, argument 2, 3. Doesn't work. So I could experiment around with it a little bit. And I can go, okay, well, what about this? What's going to happen here? And I'm going to go plus 1, 2. And then I'm going to press return. And I'm going to go, oh, I forgot to do that. Closing again, I'm going to press return again. And it's going to say MPair. So there was a contract violation with an CDR. So I'm going to show you CDR in a few minutes, along with CAR and along with built-in. And this is a given 3. Given 3, it didn't know how to occur length because length is a 1. So we have Lisp processing. And okay, so this is where CDR, CAR, and some of the cons and some of the other built-in Lisp functionality is taking over, and it's changing my logic a little bit. Because I have Lisp processing functions that are built in that are going to manipulate my list for me automatically. And it doesn't understand why you're asking it for a length when there is no length, when you're not giving it anything for the length. Because the CDR removes an item. or takes and returns just the end of the list, or does certain things to it. So it wants things in a certain logical order in order for it to process what it needs to do. Up here at the top, we can do the same thing. So down on the bottom, I'm going to leave that error message alone there, if I can get out of it. Let's see, Control C. No. All right. Let's move to the top because I've hosed my bottom. Actually, let's go stop. Here we go. There we go. Now I'm back. So up in the top window, I'm going to type the same thing in again because we have a limited vocabulary right now. I'm going to go plus 2, 4. And I'm going to press return, and nothing's going to happen. But if I come over here to the right-hand side and say run, then it's going to run for me. And you see now I have 4 plus 2, which is 6, and the result showed up down here. So on my desktop, I actually put a scheme. I believe I put a scheme function in here, but let me just take a look here. I'll load it up in WordPad. I did. I put a scheme function up here. So I'm going to show you something that's very handy, which is what people do in the real world. They go File, whoops, Open, and I'm going to pick the scheme function, and I'm going to go Open, and it's going to open up a new scheme window, and I'm going to hit Run. It's kind of down here. It says, okay, now what do you want me to do? Oh, I want you to run this file. So now I've loaded it up and I put it into memory. And what does this thing do? Well, it gives me a reply, and it wants a reply S, and S is going to be a string. So if I type in reply and the S is hi, if it's equal to hello, it's going to come back and say hi. If it's a substring it doesn't understand, it's going to come back and say, huh? I don't understand you. So to run the function, I would go like this and go reply, hello. It says come back and says hi. Because in my conditional, and just to explain functions to you, I've used the word def to define a function. The name of the function is reply, and the reply takes on one parameter, S. So I send S to reply. If, and the string isn't, the string that we're looking at is S. If it's larger than or equal to the string length of 5, it means it's smaller than a certain amount, excuse me, larger than, well, anyway, long story short. If it's equal to hello, take a look at the substring that we're pulling out of the string and come back with hi. If not, huh. So if I run the same function again, and down here I'm going to run the function, and I'm basically showing you this because I want you to see how you can run functions and how to use, it's an orientation to the environment. So I'm just going to put a big old string in here like this. Oops. And then I'll close it, and then I'll press the huh. So now it comes back and says huh. So all of what you're going to do is going to be sort of like in this kind of syntax. This is a more sophisticated way of writing, and I'm going to show you a simpler way in a few minutes. I can also come back, let's say, for example, to this lecture that we had opened up and take that factorial example. Oops, here it is here. Nice little factorial function here. I'm going to go copy. And then I'm going to go back to that scheme window over here. I'm going to paste it up here. I could also paste it down here if I want to. I can go like here and paste it right here. And press return. It just doesn't do anything. But then now I can run it. I can go here and I can say factorial, factorial. Let's do 8. And then I run it. It comes back and says 40,320. Or if I want, I can click up here. I already have it loaded, so I'm not quite sure what's going to happen. Let's just paste it in up here. If I pasted it up here, I'm going to have to press run. Run's going to run it in here. So now it reset my memory, and it ran what I put up here. It doesn't do any garbage collection, so my reply is still in here. In fact, my reply is still up here, actually. Here's my factorial underneath it. So it's not like writing a program. So now I can still come down here and go factorial 2. It comes back and says 2. Because it understood the function. And this is a little bit an easier function, I think, to work with. This one up here, the reply is a little bit. It's an example I gave you, actually, for one of the assignments that you're going to do. So what you're going to do for the assignment is actually kind of take and analyze some data, analyze some lists, do stuff to, and figure out, well, what am I going to do to analyze the results from this experiment that I've conducted. So let's go back to the lecture for a minute or two. Slapped on slide number 21. Oops, here we go. So I kind of explained the shorthand for the quote, which is the apostrophe, and then the conditional evaluation here using the condition COND. And so now we can see this definition of the function, factorial x, that we just looked at. And all of the, under the R5, S6, or whatever it's called, that the language I gave you, all of the examples in this particular lecture will work in there. So you just cut and paste them out and stick them in there, and it will work just fine. If you select one of the other languages, you may not necessarily have as much luck, but some of them will work. So what will end up happening is you'll go online and you'll find examples, and you'll take a look at those examples and you go, well, what language is this? It's Lazy Scheme, or it's Lazy Racket, or it's advanced students or something. And then usually they tell you what it is, and then you set the language correctly, because it's one language, but it really is different languages. So, but the concept of the scheme is the same, and these concepts here are universal among all of the different languages. The entire language of Scheme is made up of 6 functions. And here they are. So, in fact, the 6 functions are right here. The entire programming language is composed of these. And here they are here. 6 basic functions, the cons, the CDR, the car equals the atom, the condition. The condition you're going to use, most of the normal everyday dialects don't use it anymore. We just use if, then, else with that instead. So what are these 6 basic functions that control every function that you write? Here's one of them in particular that comes in handy. And while I'm giving you this PowerPoint stuff, if you're, bored, leave your scheme up and start typing this stuff in. Every one of these examples should work just fine. So like as an example, the car. Actually, can I flip? I can flip. So car ABC returns A. So you should be able to type in car, what was it? A, B, C, and it returns A. There's something else I forgot to show you. Spaces are important. If you put an extra space in, I'm going to go back to the +1 and 2 and show you something. So you don't put anything at the end, you just hit the return key and you get the response that comes back. But let's say, for example, I put an extra space in here. That's probably not going to matter. But in here, I go 2, 3, space, the end. Oh, they'll say it. So now, okay, so this one is going to keep it. Some of the other languages would actually come out with an error. If I could do this, go +2, 3, 2, 3, it's going to take it as 23. It's not going to take it as 2 and 3. So sometimes it's best not to put extra spaces in. This language is forgiving. Some of the other ones, the beginner student, should come out with an error message actually. If, let's do it. I'm trying to generate an error out of this. No, not going to do it. Okay, but long story short, if you're getting an error message, check your spaces, because sometimes the spacing is it's space delimited, and it's read and interpreted by your spaces. So sometimes it doesn't read the spaces correctly. Alright, so back to the useful functions, and as I was demonstrating, feel free to cut and paste and put them in there, or just type them in there. So CDR returns the list. So this returned A. It doesn't get rid of it. It just returns the first item on the list. Because what you can do is take the first item on the list, run it through a function, then take the first, get rid of the first item, use another one, use a CDR, get rid of it. Take the next item on the list, take the next item on the list, take the next item on the list. You're never going to lose track of where you're at in the list. So this is opposed to taking a big old spreadsheet, like in Excel, and going down each one of the columns, and what column was I on? It's kind of an automated way of traversing through the different columns. So car returns the first element of the list here, and we're just going to return A. CDR returns the list that results from removing the first element from the list. So you do a car A, or, you do a car on the list, and then you do a CDR, then you do a car, a CDR, car, CDR. And what ends up happening, especially if you do this recursively, you traverse through and you have an empty list at the end, because you've gone through all the data, and you've taken each item one by one as an order that comes through. And it removes it from the list. So here we have A, B, C returns B and C. CDR A just returns you the empty list, and you're done. So cons constructs a list by inserting, this is not condition, it's construct. Constructs a list by inserting the first item at the front of its second argument, which should be a list. So cons x takes, now we have x, a, b. So we just added x to it. So if you've got a whole bunch of stuff that's coming out, you take the data, you put it in, and you say, you know, cons this, and then you build the list. So you build the list up, you break the list down, go back and forth. You can also do it using the lambda expressions, and then here we have the form of the lambda L, which is car L. And L is the expression above, it's called the bounded variable. Now you're wondering, she said we don't have variables in this language. You can have variables in this language if you want variables in the language. So lambda expression here can be applied. So we have lambda L, car L, with A, B, C, D. Does the same thing. So the expression A is its value that's returned. So A to A, B, C, D. So now we can also make function definitions in the scheme, and we don't have to use names. We can actually, in this particular case, we're using names. We're using cube, but we can also use lambda expressions for the same thing. Same thing that we did here. So it's just a matter of saving, using the functionality and making the best of it. So here we have a function define, can be used to define functions, and has two forms. So here, to bind the symbol to an expression, we can say define pi is equal to 3.14, yada yada. Looks like a function call, but this is a variable now. So yeah, we don't have variables, like we don't go integer I is equal to 5, I plus plus. This is really a function call, but we're using define. So anytime you use define, this pi is actually used as a function. It just returns this number. So if I said define pi and I type in pi, I'm going to get this substituted value, because pi is not really taking on any parameters or anything. It's just going to return this value to me. So it's kind of working like a variable, but it's really a function, because this is a functional language and everything is a function. So it's kind of interesting how that works out. So here we have defining pi, 2 pi. It's just going to be 2 times pi. And to bind the names of the lambda expression here, we can define cube x as x times x times x times x. This is where we're getting this times here. So an example of running this would be cube 3. This one here doesn't. You just type in pi, and it would run for you. There's no parameters for this one. But if you typed in pi, we're just going to return 3.14, whatever it is we put in there precision-wise. Alternative way of defining it would be used to define cube lambda x with x times x times x times x. So here we have expression evaluation process that we can go through. And I don't know what happened to my bullets here, but those are bullet points. So for the normal forms, the parameters are evaluated in no particular order. So the parameters come in and they're just evaluated. You can't expect, there's no reason why you want to expect the first one, second one, third one. There's no order to it. And the values of the parameters are substituted into the function body, and then the function is running with those parameters. And then the function body is evaluated, obviously. And then the value of the last expression that is evaluated is returned from the function and sent back to the function, if we're going to essentially run a recursive function. Or it's returned to the user if it's not going to call itself again. So special forms use a different evaluation process. Special forms are going to be forms that are created by different languages. So some of the different language dialects have special forms of functions that are designed for special purposes in terms of the language evaluation. So lo and behold, we have this thing called map. And map is a predefined function call-in scheme that can operate on multiple lists of arguments. So we have map. So now we're jumping ahead. So before we had one value, one value, one value, one function call, one function call, one function call. Let's quadruple it. So now we have one list and another list. So map takes the first list and applies it to the second list. And what's it going to apply? Well, it's going to apply a plus. So it's going to take first item in one list and add it to the first item in the next list. So that's some nice automation. If you've ever tried to do that by hand, usually you have a spreadsheet. Maybe it's two separate spreadsheets and you try to add them together because nobody knows how to figure out how to do Excel correctly. Or maybe it's not in a spreadsheet, maybe it's on paper printouts and stuff. So you somehow digitize it, get it into a list form, take the list, send it to the function, get the function to add them, first column here, and get them merged together. Or you better yet, add 3 of them to it. Better yet, add 4 of them or 5 of them. The sky's unlimited, which is why you're going to run out of memory eventually. If you have a small memory footprint and you're loading in tons and tons of data, you're going to need to probably increase your memory at that point. But working memory for your examples right now is pretty small, no memory problems. Here's combined with the Lambda expression. If you like to use Lambda expressions, Lambda AB with a list AB. So here's the functional form as we remembered before. We're going to see some more examples, but these are the 3 functional forms that we saw with the Lisp. We had the composition applied to all, and then the function we just saw a few minutes ago, which is the functional form. So in the composition we have cube, and then we're going to apply towards, and then what we've done here is just nested it a little bit. We put a 4 plus a 2 in here, and this is going to be substituted. So this is a function called add, which is going to be substituted into the function called a do multiplication, which is going to be substituted into the function called a cube. So we can basically break it down from all of its different levels. And then they apply to all with a map car. So remember that map car message we saw kind of, I don't know, about 20 minutes ago or so when I was typing stuff in? It thought I was running a map car because of the syntax that I was using. It was expecting something but didn't get that. So the map car cube, if I actually typed in map car cube and ran this, which is a very similar expression to what I put in before, it takes each one of the expressions and applies it towards the function. So the apply all is basically the map car. So the function map car that applies to a function to all of the elements of a list. The value returned from map car is the results of each one of the list items being processed through the function that we're running. So it thought I was doing a map car. I sent it something like this, but I think I did plus or something. I'm not quite sure what I did. But the syntax was supposed to be apply each one of these items, apply all to this function. So sometimes it comes back with those cryptic messages, and you look at the message and you go, oh, what are you talking about? In this particular case, when I saw map car, I went, oh, that's what I was doing. Wrong format. So it's possible to define functions that build scheme code and request its interpretation at the same time. And we have this thing called eval. So we can put an eval in here, evaluate an expression, and then use it for an else. So it's basically explicitly telling us to evaluate it now. Don't wait, just evaluate it now. So you're defining a function that builds a scheme code and then requests its interpretation while the function is being run. For example, suppose we want a list of numbers that must be added together. The parameter is a list of numbers to be added, adder, which is the name of the function, inserts a plus operator and evaluates the resulting list. So in this particular case, we'd be running it with adder 1, 2, 3, 4, 5, which is going to return 10 in this particular case. You don't have to write anything that sophisticated for the programs that for the stuff that you're going to write for this class. So now we have apply. So now the scheme function apply invokes a procedure on a list of arguments. So apply plus returns 10. So because we're going to take 1, 2, 3, and then we're running a function call and a function call, but because we're saying apply, we're taking this as a list, and this is the key here. Because if not, we could just put the plus in front of here. We could rewrite this whole thing and go, but then we'd add everything together if we did plus 1, 2, 3, 4, 5, because we do it that way. But we could nest this inside of something else if we wanted to, and then this could be populated from another function call if we wanted to. So it depends on how you want to write the function call and what use you're going to make of it as to how you're going to write the expression. But the apply comes in handy, I would say. We also have imperative features, imperative language features, so we can set a variable which binds a name to a value to a name. And we can do with a set car replaces a car with a list, or set CDR, which replaces a CDR of a list. So here's some examples. We can define A as 1, 2, 3. And when you type in A, you'll get 1, 2, 3. Why would you want to do that? Well, if you don't want to keep writing in a whole big list of stuff, and you know that this is, you got 20 items in a list, and you just want to call it A, and then you could take A and add it to B, or A and subtract it from C, or something. And actually experiment. You had your question earlier with a negative number. Put a negative number in, it just works like a number. It's a regular old number line. So I just remembered, for some strange reason when I saw this, I remembered your question. So this, at least 1, 2, 3, these are the line numbers, by the way, so you're not going to get that. We've seen what it looks like. GNU scheme has the line numbers on it, which is interesting. So your different scheme dialects are going to give you a slightly different interface. In fact, the GNU scheme I don't believe has the split screen, but it might now. Older versions of it ran from a terminal prompt. So you just typed in from a terminal prompt. You just put your stuff in there and it works for you. So here we have cons 10A. There's going to be 10, 1, 2, 3, A. And you notice it says, well, what happened with A? A is still 1, 2, 3 because you defined A as 1, 2, 3. So although you're using it like a imperative language, you know, like C or C++, you're calling it A, you're not changing A. So if we did this in C, we said A is equal to 1, 2, 3. Okay, so add 4 to A. A would be equal to 1, 2, 3, 4. In scheme, A would still be equal to 1, 2, 3 because we defined A as 1, 2, 3. So it's not really a variable, it's a definition. So we have cons 10 to A. Well, cons is just going to put in front of this one here. So we have A. Set car, A5. Now we're going to set the first one to 5. Now we're setting it. So the set in front of the expression actually changes the value. So we set it. So instead of 1, 2, 3, now we have 5, 2, 3. We type in A and we say 5, 2, 3. So the way this works actually is the list schematics work with a list. So remember I did this entire talk talking about Lisp. And I said Lisp is a dialect of scheme. It's also a dialect of common Lisp. Lisp is a list language. For those people who know C++ and are familiar with the concept of the linked list, it's a linked list. And it's all stored in memory, which is how you can fill up the memory. Because it's all going to be linked together. Nothing goes away, there's no garbage collection until you get rid of it. So here's what happens, and this is what happens in terms of the standard linked list. We have nodes, and each node has a tail, and then has a pointer to the next node. And then we have, you know, the next goes to the next node. But we do not have to use pointers in this language. It's done for us automatically, but it's implemented kind of like pointers with the memory that you have assigned to the environment. So the list is an S expression that isn't an atom, it's actually a list data structure. The list has a tree to it. So we have the head and the tail. And so here if we have a list of A, B, C, and D, it looks like this in memory. So we have A, B, C, and D, and A is the top. So when we do cons, it just says, find the first node, remove it. Find the next node, remove it. It doesn't know what's in the node. So it's not in the lecture set here, but I have to mention to you that A, B, C, this could be a function call, the number 1, character, a float, a double. Put anything you want in this list. It's the same thing you get with C++ with linked lists. It's just memory locations storing an item. Who cares what the item is? Just put something in there. So you no longer have to worry about all the restrictions that you have with arrays and other list structures in other languages where it all has to be the same data type or something. Doesn't matter, it's all linked memory. Has no idea what's in there. It doesn't care. So now we have note that the empty list is the probably, well in this particular, I like to look at it upside down and call the empty the root, but in this case it's the tail of the tree. So when building a list, this is how the cons, the CDR, and the cars actually work with this. Primitive function cons, which concatenates a list to a list, which is what the CON is short for concatenation. Concatenate an element to the list. So here's the element, here's the list. So if we said cons A to ABC, we'd end up with ABC. So con A to AB to BC, A to BC, we get ABC. Hopefully that shows up for you. Oh, it does. You can't really see the color on your screen, but this is a blue or cyan, and this is an orange color. Cons A to the empty list gives us A. Now we have an empty list A. Cons B, A and B with C and D, so A and B with C. Now we have them both together, so we just have this tie that makes them together. So it's basically just doing concatenation from list item to list item when we do that. We have car, so accessing list items themselves. Get the head of the list. So it's kind of like saying, give me head, give me head, give me the head, give me the head, or give me the tail, depending upon which direction you're traversing through the list. but this works with the front of the list. So car selects the left subtree. So if I said, car ABC, well, it's going to be equal to A. Car A, which is inside of ABC, well, we got A, which is the first item that's going to be in there. So it's basically, for those people who are familiar with linked lists, you're working with a linked list, a primitive version of it that you're not creating yourself, but that's the data structure you're working with in Lisp, and also in Scheme as well. So accessing the list components, get the tail of the list, CDR. So we have the head and the tail. CDR selects the right subtree. In this example we have CDR ABC, well, it's going to return B and C. It's going to do the opposite. So it pulls the head, and then it gives you everything else past the head. So it knows what's there. It doesn't actually know what's there. It just pulls whatever's in memory that's linked up to it, which makes it fast. Because going through the concept of searching and sorting through a list, it's easier to go through it blindly and just take everything than it is to actually go through each one of the items, especially if the search space is big. So here's car and CDR in terms of deconstruction. So car and CDR can deconstruct any list, and so we can put this combination together with combinations. So we can go CDR, and we have a car on the back. So we're going to get the tail, get the tail, get the tail, and then, get the front. Which is why I was saying before, you do a car, a CDR, a car, a CDR, a car, CDR, and you can actually just go through each item, one item at a time. So special abbreviations are here for sequences of cars and CDRs with the C and the R. One of the languages supports special abbreviations, and those are the special abbreviations. One of the teaching languages, actually, when it said with abbreviations, this is what it's referring to. Instead of, because it's really hard to type in CAR and CDR, it's easier to type in C and R, it's one character. So it's kind of like Linux people, Unix people, It's all hand done, so there's shortcuts and there's ways of habits that people get into, which is why we have so many dialects. Because, they just write the new dialect, and you just put it in, and it's a language file in the form of a text. What it is just a lookup. It means this is equal to this is equal to this is... It's kind of like you could take everything and rewrite your own syntax, but it's all the same expressions. It just has different expression names. The form of the expression is identical regardless of which language you're using. The language is just a dictionary lookup of all of the commands that you're using. Because some people like DEF instead of define, because they don't want to type out define. Well, get some of those crazy languages, and you can write your own language actually and have people use it. So, let's see, using car and CDR. If you're doing that, you just contribute to the GNU license actually. And you put it out there, and all of a sudden people are going to be using the ITU language. Everything starts with an I. ICDR, ICAR, IDefine, because of whatever. And actually, believe it or not, there's languages out there. So. I don't think we want to widely distribute that, though. It might not make us look too good. So. Alright, so the car and the CDR here. Here's an example. Most scheme functions operate over lists recursively, and here's our recursive list, where we're taking length, and at the bottom we're running length. Usually you see the recursive call at the bottom. And here's just two examples. One's doing a sum, and the other one's calculating out a length. In this particular case, I just run the length, but we wanted to create a new function called len instead of length. So we wanted to write our own function. So this was going to return the value of 3, this is going to return the value of 6 because it's going to do the sum. And basically this is the call here. This is the function call at the end. In here we have the recursive car and the CDR that's being run on sum. So it's calling sum and doing a CDR on one item of the parameter that's being sent to it. So down here on the bottom is the function call. The function above it is doing the recursive call here with length as an example. Some useful scheme functions. We actually saw a couple of them already. The plus, the minus, these are functions. They're symbols, but they're just same thing as typing in ADD, minus. It's the same stuff actually works. Different dialects for different languages, obviously. Equality, we can use EQ question mark. Is this equal? This one and this one? So we can see, did we get the same results every time we do it? We can take thousands of numbers and through this list and say which ones are equal and come out and say, hey, 50% of them are equal. Oh man, we're on the right track. We're heading towards the right direction with our research. Or is it null? Is it empty? We can test for an empty list. We can also do type checking on a list to say, is it a list? Is it a sub-expression? Is it an atom? Is it a name? Is it a number? Is it 0? Did we get anything out of this? And it come back and says 0. Sorry, go back and try it again. We didn't find anything that matched. We can also make list arguments and make an argument into a list as well. So we can take list A, B, C, and it turns it into a list. So if we don't have the data into a list form, we can make it into a list form as well. So how this game really works, it does a read, evaluate, or print loop. So it reads the information in, evaluates it, prints it to the screen, comes back in, reads more information, evaluates it, puts it back to the screen, reads more information iteratively until it runs out of stuff to do, and then it just sits there and blinks at you. It just sits there, it doesn't really do anything. So in a particular case on the evaluation for the input, we've seen this, so I'm not going to go through the more intricate details of this. And I'm not going to go through the rest of this either in terms of the read, evaluate, print loop, because this gets a little bit dry. But I will talk about polymorphism for a second, because that's what I was mentioning before. It doesn't really matter what's in the list. So we have polymorphism, and this is not an object-oriented programming language, by the way, either. It's a functional programming language. But we have polymorphic functions that can be applied to arguments of different types. So as an example, the function length can say a function of numbers, length, give it numbers. Length, give it characters. Give it a combination. Doesn't know what it's getting, doesn't really matter what it's getting, it's just counting items, or atoms. We can say function 0 is not polymorphic if we're saying 0, 10. So we have some functions that are polymorphic, some functions that are not. It depends on the design of the function. And this applies to your user-defined functions as well as the built-in ones. So if this one said 0, 10, and a 10 was a string, it'd come back and say, I'm sorry, I don't know what you're talking about. I don't know if I'm 0 or not because I'm not a number. And there's no types, so it takes a look at the data and it determines the data type by what it finds. So if it finds a string, then it says, oh, I'm a string. If it finds a number, automatically we're a number. So it's kind of interesting that way as well. So 0 with an object, the object is not the correct data type. It doesn't know if it's 0 or not. And here it's coming back true or false, actually, as a value either equals or 0 or is it there? So we can define global variables as well, but by default everything is static. So a predefined function define merely associates the name with values. So define moose as ABC, then we go moose. Define yak, define all of the, basically what it's doing is creating a local variable name that's associated with a formula or a function calculation that you're willing to do. Makes it global once you load it in and you've got it. In fact, if you load it into the top screen, makes it all available. But in terms of variables themselves, think of them as function calls or identifications and not necessarily variables in the traditional sense of programming. We also have the unnamed functions as we've seen, but it's really hard to run an unnamed function. So you run the unnamed function with the data automatically, and then it all works correctly. But so here we have functions that are values. And how would we do that? Well, the function can exist without any name if it's just a value. The function is add something up, divided by this, and do something else with it, and then send that to factorial. So we have some instances in which we don't want to commit to a name. Too much work. We're never going to use it again. We're just going to run it once. It's going to be a parameter to a function call. And don't bother giving it a name. You don't have to. So the notation is based on the lambda calculus as we've seen before, and that's the formal form for defining the recursive functions and their properties. A lot of recursive functions, we're going to have functions inside that are just going to be calls to itself. They may not necessarily need a name. Here's some examples. The times 10 by 10, we can define, in fact over here, the alternative form of the definition, where we've got define square x, lambda x, but we're going to say define SQ, but we're going to use lambda x instead of square x in there. And it's going to basically have the same functionality, but we're calling it by SQ. Here we've defined it as square x, but it's not necessarily being used. Anyway, it depends upon whether or not you want to put names in there or you only want to have an unnamed function. So functions in Scheme are all high order functions or higher order. So the functions can be returning values, and they return once per function call, and that value is substituted in. So define double n, treble n, quadruple n, etc. and so forth. Or define, and then here we go, a value to itself. So we can evaluate which one it's going to be and run it, essentially. Alright, so we don't really need to know that much about higher order functions, but they can be used, again, functions can be used as parameters as well, just to reiterate that point. And functions as parameters, considering these functions here, we can insert them in different ways as parameters, named or nameless. We can also put different numbers in. We have negate here, it's going to give us the opposite actually as well. So. Then we have double, invert, negate in terms of the function calls. So where are they different? Well, the same function, it's just that they're using different function calls themselves. It's really the same function over and over again, but, well, for the functionality. Environment, so a special form of the let and the let with the asterisk are used to define local variables. So if you really want to define a variable, you can say let A is equal to 1, 2, 3. Well, better yet, just say A 1, 1, 2, 3, and the function A would return 1, 2, 3. So both establish binding between variables and expressions. So let does binding in parallel, and the let with the asterisk does the binding in the order in which you give it. So that's everything you ever wanted to know about Scheme. And lucky for you, the next assignment's not on Scheme, but the last one is for today. So I'm going to pause this video as soon as I can get back out here and go over the assignment next.